So in this lecture segment, as part of the module on causality and observation versus experiment, we're going to talk about, can observational studies prove causality? So Bradford Hill, who was one of the authors of the Dahl and Hill papers, gave this a lot of thought. A lot of other research that he did was addressing working in certain occupations and whether that was associated with certain types of disease. And then he did the smoking and lung cancer work. And so many people dismissed his research and said, but this is association. This is not causation. You cannot prove causation. And so Bradford Hill actually wrote a paper that was sort of a commentary. Well, what should we be thinking about when we're looking at observational data to see whether there is causality? So the first thing he said was, well, what is the strength of the association? So we saw that in the British doctors cohort, the deaths from lung cancer, the incidence was more than 10 times higher among the smokers than the non-smokers. So that is a strong association. So the reason why a strong association is important is that it's difficult to imagine any bias that could have been built into that study that would result in an association that strong. So the real importance of strength is not that we think that all true cause and effect relationships have a strong association. Many diseases are multifactorial, and any individual risk factor does not have a strong association. But if you can find evidence in a study of a strong association, it's harder to argue that a bias or an error in your study design led to that result. Consistency, meaning consistency across different studies. And we didn't show you all of them in the lecture, but there were quite a few other case control studies that showed consistently this association between lung cancer and smoking. And of course, something that to this day you'll also hear is, but what if the apparent consistency in the literature is just the result of publication bias? That's still a tough one, but the idea being, if one study finds a result, that's one study. In observational research, if there are multiple studies, that really makes the evidence much stronger multiple studies with consistent results. So specificity, and this would be the slide where the association of smoking with lung cancer was very strong, but with other cancers less so. So that specificity, if there was some bias or confounding within the study that made it look like lung cancer was associated with smoking, wouldn't it have also made it look like it was associated with other types of cancer? So temporality is just, are we sure that the putative cause actually was present before the effect? So we think about Dr. Fisher saying that, well, he thinks that people had early stages of lung cancer and started smoking more because smoking is so pleasant and soothing. And so that's that reverse causation issue. And there's actually a lot of other types of clinical research where you have to read carefully and think about what they did. And sometimes they can't truly establish temporality, that what they think is the cause was really present before the effect. When people are using sort of large data sets and electronic data, do we really know the direction of temporality of cause and effect? So biological gradient in this example would be the number of cigarettes per day that we saw. The disproportionate cases compared to controls was particularly strong at the highest levels of smoking. Plausibility is a great one. So they had to admit throughout the 1960s and later, we really don't know what the actual agent is, what the biological pathway is that is creating the lung cancer, or how cigarette smoking would contribute to that. So not every study or set of evidence is going to meet all of these criteria, except that smoke is inhaled through the lung, and it's the lung that was getting cancer. That's the plausible part of it. Coherence is coherence across different types of research or related cause-effect relationships. Experiment. Of course, experiment, many people to this day would say a good experiment is going to trump all of the observational evidence, but is there some experiment that doesn't prove the whole of it, but that proves some aspect of it, such as the formation of the adducts in the DNA. And of course, he's writing these 9 criteria long before the DNA study, decades before. And then analogy, that's, to me, that's kind of like plausibility. I don't know why he thought he needed 9 criteria, but anyway, they sound like the same to me. Okay, but a message from Hill's article. So if you go and tell certain people who are epidemiologists that in this class you learned about the 9 criteria, some people will say, oh my goodness, 9 criteria, that old canard. There aren't really criteria. Do people still teach that? But actually, Hill's article thought those were useful principles, but then he went on to say he doesn't believe that they're criteria either. So he says, what I do not believe is that we can usefully lay down some hard and fast rules of evidence that must be obeyed before we can accept cause and effect. The fundamental question, is there any other way of explaining the set of facts before us? Is there any other answer equally or more likely than cause and effect? So is it our responsibility as the epidemiologists to prove cause and effect, or is it our responsibility to do well-conducted studies, provide evidence, show that that we have really addressed in our study the possible biases and confounding? We don't think that that's what caused this result, and therefore you do have to take cause and effect as a likely reason for our results. He actually went on to quote Sherlock Holmes and Conan Doyle. When you have eliminated the impossible, whatever remains, however improbable, must be the truth. So when you have eliminated the impossible, or when you have eliminated other biases and confounding that might have created your result. So what else might explain an association? We can say that we see an association in observational study, and we're very careful with our language. We say that this is associated with this is associated with this. But are we really able to say this, that A caused B based on our data? What other possible explanations do we have to rule out? So the first one is chance, and in your experience in our master's program, you'll have plenty of statistical classes, and so those will go more into the role of chance in research, but you want to have adequate study power and sample size to reduce the role of chance in your results. You want to be able to say that bias from uncontrolled confounding is not a possible explanation for your results. Selection bias and information bias. So these last 3 things are concepts that we will go into in a fair amount of detail in this course and in subsequent epidemiology courses and throughout the epidemiologic literature. We like to talk about, is the study possibly influenced by bias from uncontrolled confounding, selection bias, and information bias? And those are 3 key concepts that will be recurring. So the 9 criteria seemed a little redundant to me, and your textbook for this course has a summary which is a little bit shorter, but the same concepts still keep coming up through the thinking of epidemiologists over the years. Is there temporality? Does cause precede disease? Is the association strong? Is there no possible non-causal association that would account for the association you observed? Is there a plausible explanation for the association being a causal one? And is the magnitude of the association strongest when it is predicted to be so? So often you'll see these points, the temporality, potential biases, confounding, strength of the association. You'll see these issues addressed as potential limitations in the discussion section of a paper. And ideally, of course, you say something is a potential limitation, and then you go on to say, but why you think this limitation is really not very much of a limitation because you did such a good job with your study design. So in the discussion section of a paper. These are also useful things to think about in a grant proposal when writing your strengths and limitations. So we don't like to call these criteria, because that's very, people will think that you're too simplistic of a thinker if you say you have criteria. But you can talk about strengths and limitations and these issues that may affect ability to draw cause and effect conclusions. So for this module, for these lecture segments, some take-home messages. First one is that when you're evaluating observational studies, you need to think about the study design. Given the design of a specific study, we then ask what factors other than causality may explain an observed association. So in fact, I'd like to say that by the time you've taken an epidemiology course from me, when you go to read an article in the literature that is based on an observational study, I'm hoping that you will spend more time reading the study methods. I think that observational studies are susceptible to biases and confounding, and you want to scrutinize the methods of a study to see how well they have avoided those issues. So besides just, I know that we're all in a hurry. You want to look at the abstract, look at the tables and figures, and not read too much of the words. But I'm going to encourage you to think more about study design and read more of the study design section, of the methods section. Take-home message B. We will spend a lot of time in this class discussing issues of confounding and bias, because these are the alternative explanations to cause and effect when you have an association. Take-home message C is that a well-conducted randomized trial is free of most of the biases of observational studies and therefore provides better evidence of causality, and most people would agree on this point. And then take-home message D, however, there are many clinical questions for which a randomized trial will never be conducted. This may be due to ethics, feasibility, or both. So taking smoking and lung cancer again as my example, will anyone ever randomize people to smoke 40 cigarettes a day for decades and randomize other people to not? Well, first of all, today, ethically, we would think that that would not be responsible because we feel like the evidence is already strong enough and that we wouldn't want to expose people to harm for the purposes of our research. And that study would also be infeasible because there are people who might be randomized to the non-smoking arm who, it turns out, are going to take up smoking and become addicted to it. And there's going to be other people who are not going to want to participate in the heavy smoking arm. So both feasibility and ethics affect our ability. And there's also the fact that you would have to follow this randomized study of smokers and non-smokers literally for decades. And in terms of a researcher conducting a study, I don't think that would work, and I don't think you would ever get funding to do that. So again, there are many clinical questions for which a randomized trial will never be conducted. So we do need to evaluate and interpret observational evidence. So going forward through your epidemiology courses, this is what we'll be working on, is evaluating and interpreting observational evidence.